So task 3 is due Thursday. The PCB part of it, you have done the most part of the PCB for task 1 or 2. And if you go to my website here, I already included pretty much all the rest of the parts except for the SD card socket. So if you go to Dr. Carlson's website to find out the BOM list of the board here, where can I find it? Is that lab 1, I think? Usually lab 1, lab activities. Let me search. Right, so one of them is a link. Okay, click it, you'll see all the parts being used for the pigboard. So the socket he used for our pigboard is too expensive. It's not available immediately from DigiKey, so I have to use the Amazon one, which is probably like 10 times cheaper. And if I order, Kate already ordered today, so we'll get it probably on Wednesday or Thursday this week. Is that amazing? So all the parts will be ready. And I will post a tutorial on how to do the SD card socket to my website as well. So all the parts that you need to use for the pigboard should be all available on my website. But if you have questions, you can always ask me. For example, how do you make a package for the ultrasonic sensor? What about that? Ultrasonic sensor. Do we need to spend a lot of time on that or no? Just give you an example, okay, for PCB design. It's actually easier than you thought. So let's take a look. Is that number 11? What's the number of the lab? Just here, ultrasonic sensor. Okay, so this one. This guy. Just for example, okay, applies to all the other groups as well. Do you need to find out the HR04 parts in Eagle for this guy? It's just 4 pins. So on the PCB, just basically 4 holes. It just needs 4 holes. Okay? So in that case, and the distance of the holes, you can see this female connector is comfortably connecting to these male connectors, the pin headers. So basically, it's a standard gaps in between the holes. So you can directly just use the connector, the 4-pin connector we have been using. It's directly one of them, and add a silk screen label next to it, and label it as HR04 ultrasonic module. That's it, just 4 holes. The SD card one's a little bit more complicated because depending on which socket you are going to use, there are just like 4 holders and several pins with a different distance, different alignment. Getting complicated, and there are so many different variants. So I have to look into the layout or the pin out of the socket I ordered from Amazon and design the socket by myself. And I'll probably just upload that library file to my website so you can directly download and copy and paste to your folder so you can directly use it to make things easier. Okay, and you have already had the experience with task 1 or 2 for the PCB. So that's why I'm thinking it's really feasible to have a deadline on Thursday, even though I know there will be still some pressure on it. But if you cannot finish on Thursday, I can still help you probably on Friday morning during office hours, go through your PCB design. I'm hoping to get everything submitted on Monday, so it takes about 7 to 8 days to receive the board. We'll see. Okay? So have a first deadline on Thursday. If not all the students can make it, I'll just make an extension. What's that?
And for the code that's due on Thursday, we're testing that with the current pigboard we have.
Yeah, it's a draft.
Okay.
There's no way that I can test it. Just got a big picture of the code.
Okay.
80% of it or something like that.
Sounds good. Okay.
Yeah. Doesn't have to be accurate. There's no demonstration, right? There's no demonstration. It's just a draft. Could be like 10% pseudocode. Just trying to plug in your ideas into the code and get a big picture, a big frame of the code. All right. So if you look at the time here, the timing, the demonstration on the pigboard is about like 2 weeks from now. So you have a lot of time to work on it. And so this week we are here, right? We're here. I'm gonna do 3 more lectures this week, and 1 more lecture on Monday. And I will let you work on a project on Wednesday and Friday. No lectures. I'll be in my office area if you wanna come and visit. We're able to discuss on some of the technical issues. So you are given the time to work on it, right? You wanna say, Dr. Lee assigned a lot of projects on the top of 2 more labs and never give us time to work on it. That's not the truth. That's not the truth. That's not the case. I'm giving you time to work on it. So 1, 2 lecture times, 15 minutes for each, and 3 here, right? So it's 3 lecture times, and I got a lab time on the 21st. So 22nd will be the first time we do the demo on the pigboard. I'll let you guys sign up. So we actually have 1, 2, 3. Okay, because if we give like 2 minutes for each group, you do the math. 60 groups. It takes about 120 minutes in theory, right? So in the middle we have the transition time. So in the future probably, so when we're doing the demos, I'll probably just let students line up over here, right? So get ready on your boards and do the presentation for 2 to 3 minutes, run the demo. We'll see how that works eventually. Okay.
So for the presentation, should we?
Slides, right?
Slides
Got a slide. Yeah, I'll get a slide. We'll see. 3 slides, no more than 5 slides.
No more than 5 slides?
Yeah, we'll see. We can do 2 minutes, 3 minutes, or 5 minutes, depending on how I want to do it. Okay? I'll think about it. Still have like 3 weeks to make a decision. It's okay. But definitely, as you know, there will be a 3 to 5 minutes presentations at the end. And you'll have slides, slideshow, and also demonstration in real time to just get it ready. So this week we covered some of the things we didn't get a chance to cover, and Lab 10, and the I2C and accelerometer modules. So for a lot of people work on track 1, I hope you can start working on it as early as possible. So that's why I want to cover that this week and including next Monday. We'll get the pinouts, the registers introduced, and give you the parts so you can start working on Lab 14. You don't have to wait until this time, so you can have more time to work on your projects. So Lab 14 will be, there are 4 or 5 different projects listed by Dr. Costin. So remember, we have a flyer, right? So according, just refer to the flyer here. So for track 1, you just have to pick up one of the listed projects in Lab 15.
And for those, will you be giving us the accelerometer?
Yeah.
Okay.
Yeah. Did I send an email to the announcement? Post the announcement. The parts, I already grabbed the several parts of the MPU modules in my office, so you can come and pick it up anytime. So I'll be there during my office hours. But if you make an appointment, you just email me. I can give it to you anytime. Okay? Is that clear on the plan for the rest of the semester? Okay. So let's get back to Lab 10 since we have a lab this week on Thursday. So Lab 10, I made it pretty easy for you guys because just want you spend more time on your projects. As you can see, it's almost everything's given. And we talked about this a little bit last week. What's that?
So is that like as given for the Colston thing? Because like with the code that was given last time was not what was required by the TAs. Like I came into the lab, I had what I thought was working based on what you said and based on, I don't know, but it was not enough for them. So is that based on the lab, or is that just based on your requirements?
What do you mean based on? I mean, so the goal is to make it work, right? And I send the solutions to the TAs, so they should have the solution to help you out. What did you mean?
I don't know. I came in with like based on what you'd said in class and the code that you provided, it was like done. But when I showed it to the TAs, they were like, "This isn't working the way we want it to." Like it wasn't. I don't know.
Oh, We had a meeting on Wednesday to talk about the requirements, but just probably sometimes two of the TAs had a meeting during the meeting time. But email me if
Okay.
you have any questions, if there's any gaps between my comments and TAs, right? Just want to make it consistent. So I have the rubric in the grading system, in the Canvas. So when people are grading the work, they should look at the rubric.
And we can see the rubric as well, correct?
Yeah, it's in there.
This time.
So the demos I listed step 1, step 2, step 3. That's all the demos you are expected to run in front of the TAs. I'm going to email the TA one more time to make sure that we're on the same page. Okay. Right. Thanks for bringing that up. For here, remember in lab 10, we were able to take out bytes from the SD card and play them through the speaker. So these are digital signals, but speaker requires a analog signal to play something, right? Play a song. So the question for you guys is how that works. How can we output a digital signal and play an analog sound through the speaker?
Digital analog converter.
Yeah, it's a type. It's could be considered as a type of DACs, but we didn't use the DAC module over here. If we look at, let me see here. It's implemented by a low pass filter. I mean, since I had experience, so after I was looking at whatever Dr. Carlson put on the website, I immediately know what he's trying to let you guys to learn. Okay, so it's outputting PWM waveforms from the PIC chip, but eventually, like we see from the LEDs, right? So you output a PWM, but eventually it's outputting a analog voltage values or levels. Okay, but for the speaker, it's running different. So we have to use the low pass filter. We have to use the low pass filter to filter it out to make a sine wave or whatever the sound wave looks like in analog form. So the way that works is really interesting. So if you look, I think this is the best figure to show that concept. It's called digital signal synthesis, digital DDS, right? Digital signal converted to analog signals, and the way to do that is through a low pass filter. So if you look at here, the best way is to show you an LT-SPICE simulation, Okay. So you have learned time delays, right? If I give a pulse like this in the digital system, what's going to happen? Input, this is the input. What's the output looks like? It's input. Output looks like what? No, it's actually, so there will be a time delay because all the transistors have capacitance, parasitic capacitance. So there's a charging up the caps. So it won't be perfect whenever you provide this one to the signal like a clock or the digital signals. So whatever being received or the response from the output looks like this. You agree with that? And it's a very good interview question. So for a very simple RC circuit, a passive RC circuit like this, if you take 50% of the voltage ranges and you mark it like this, it's called time delay. It's a time delay, okay? Because this doesn't require a lot of calculations, so it can test your background really well. So they just put this on the interview questions, ask you what's the TD, what's TD? If these are given, what is TD? Keep in mind, I mean, even your teacher didn't tell you, but this is super important and fundamental. The 0.7 RC. We can do the calculation really easily because this is a step response. Just use the equations, get a 50% of the voltage range. This can be easily calculated. But, after we find out this solution or this conclusion, we don't derive it anymore. We just directly use it. It's a constant. You just have to know this as an electrical engineer, fundamental. Okay, like you know 1 and zeros. You just have to know the time delay for a digital signal like this is 0.7 RC. All right.
Is this part of the op-amp system?
No, there's no op amp. It's just a passive low pass filter. I'm so sad your teacher didn't teach you. It's just so important. 0.7 RC, okay? There's a time delay over here. So what's the rising and falling time for this guy? If he's asking you the rising and falling time. Because this is perfect, because it's the input. Consider, for example, we consider this probably only like 1 picosecond rising time. If you zoom in, like zoom in, so it becomes this, right? Okay? Just consider this is 1 picosecond. We can ignore that compared to like a microsecond level. For example, here is 1 microsecond, okay? This is nothing, like a million times, 1 of the million times of this whole period. This you cannot even realize it. So this is considered as infinite amount, infinite, right? So it's just get to the top really quickly. And then, how do you find out the rising time of the output for this one? What's the way to calculate it? So you find out the 10% from 0 for the voltage value and 90% from the top, or from the bottom, sorry. So it's between 10% and 90%, and that's called T-rise. T-rise. And there's an equation to calculate it. I think it's given in the Carlson's website. So you can directly plug in the numbers. I think that's like 0.22 RC or something. It doesn't matter, it's provided. So there's the question in the in-lab 10 asking you to find out the T-rise. So you probe it for the low-pass filter. This is just one example, okay? So the low-pass filter you are using is different. It looks like this.
What's an IPS? What is that?
LPS. 1 PS is 1 picosecond.
Oh.
1 picosecond. So the low-pass filter you are going to test for in-lab 10 is this guy. So provide the input and test the output. Make sure you don't probe here, okay? Probe here. And the corner frequency of this guy is given. You don't have to derive it. It's over here. That's a second order low pass filter, and they're trying to make all the values equal, so it's easier to calculate. So it's basically 1 over 2 pi square root of R1, R2, C1, C2. Just all the R's and all the C's. R1, R2, C1, C2. I think this is a DC gain here, but it's not being used for the corner frequency. Okay, so for the in-lab question number 1, it's easily to find. The R's and C's are equal, so it's basically R squared and C squared. So when we do the square root, it becomes 2 pi RC. Okay. So the corner frequency of this second order low pass filter is 2 pi RC. So what's the benefit of using the second order low pass filter compared to the first order low pass filter? Where's the first order low pass filter? Here, right? Which is this guy. This is the second order low pass filter. So the performance is way better because the roll-off rate is doubled. So for the first order, for example, you are getting this. It's a high frequency roll-off rate is what? 20 dB. 20 dB per what? Per decade, right? But for the second order, it's just rejecting the high frequency parts really quickly or faster. So like this. So this becomes so the second order, the first order. The second order becomes 40 dB per decade. So high frequency noise is getting rejected quickly, depending on their frequency range. Better performance, right? So now let's come back to this problem. So see, here's a time delay, right? So this time delay limits what? Frequency, because your clock frequency has to be a lot larger than this. What if it's shorter than this?
It won't even rise.
Yeah, so let's see. This is the input, right? Let's make it faster. like this. If the frequency, so the frequency is way faster than this guy, but you can compare the width, the pulse width here is a lot shorter than the time delay, okay? So what's gonna happen?
It's gonna
So-
go up and not get all the way to the top and then have to go down.
Yeah, so it's basically the circuit, the property of the circuit is not changing. The RC is still the RC, same RC in the circuits, right? But the thing is you are speeding up, you are increasing the speed of the clock or the digital signal. So you can see the time delay whenever you just charge the whatever the peripherals for this amount of time. What's happening for the output? It's only arriving here, right? It's not arriving the top, so it's not fully charged up. Did you see that? See, this is what the output is gonna do. It's just arriving here. It's not going up anymore, because at this point it starts discharging. So whenever it starts discharging, it comes back like this, right? It's way faster. So when it's discharging, this one is not keep going up anymore. What's the output looks like?
It's gonna go back
It's
down.
gonna go down, right? But the thing is, you are not even fully discharging. You are not fully charging up the peripheral parasitic capacitance, and you are not fully discharging the parasitic capacitance as well. Do you understand what I'm saying when I'm talking about parasitic capacitance? So all the transistors, right, like CMOS transistors in the CPUs and everywhere. So it's a CMOS world right now. So everything's based on CMOS. You got a gate, you got a drain at a source, right? So what's in the gate is dielectric material. So immediately you form a cap. It's called CGD. It's a capacitance from gate to drain. And you immediately form another capacitor over here, CGS. These caps don't exist. It's just a part of that capacitance from the gate to the substrate. If something exists in the physical world, you cannot change it. That's why we cannot run a certain technology of the chips at a higher frequency. For example, can you run a 500 nanometer technology, which is a 40-year-old technology, at 10 gigahertz? There's no way you can run it that fast. Because the transistors are huge. So for 500 nanometers, so the node, the size of the node is the length. So that's the channel length, which means the smallest the transistor you can fabricate on the wafer is 500 nanometers. But now it's what? Now it's like 5. TSMC is doing 2. So you can imagine 40 years ago, the average transistors are like this big, right? But the modern technology, the CPUs in your smartphone is probably like this tiny. You can compare from this for one transistor to this little tiny transistor, so you can scale down a lot, and you can integrate billions, like hundreds of billions of transistors in one very small die area. So that's why 40 years ago you can only do a LCD display for your phone, right? But now you can play a video on the phone. That's the difference. So it's limiting the clock frequency. So if you are running this faster, it's not able to fully charge up to the 5 volts. So eventually you are not seeing a logic 1. This is a problem. So you're not getting logic 1 zeros. However, it becomes useful. So the issue here becomes useful. Becomes useful. For what? For our speakers. That's how that works. So you inject your digital signal into a low pass filter and don't let it charge up. So eventually it starts oscillating. Okay? Charge up, not fully discharged. Charge up, not fully discharged. Charge up, not fully discharged. So if you modulate your pulse width PWM waveforms, make it wider, smaller, you can eventually generate a analog voltage. It's a pseudo analog voltage at a certain points. So eventually, if you, for example, this is it's the same frequency, right? Certain frequency. So eventually, it will stabilize and give you a DC voltage. But however, if you create something like this, could you tell the PWM are changing? Duty cycles are changing. See, these are wider waveforms. It's hard to tell, but let me zoom in. Could you tell these are wider waveforms, and these are narrower, and here is probably 50%, and here's 86%. And eventually you are generating a different DC voltage output for that certain duty cycle. Okay? If you design the PWM duty cycles carefully, and eventually you can create a sine wave. So see, this is probably this is rising, right? And then you can design another series of PWMs and discharge it. So eventually you can create all different kind of frequencies depending on what kind of duty value you provided to the PWMs. So it's basically an issue for digital circuits, but it's being useful for DDS. What's the form of DDS? What's the first, second D? Direct digital synthesis, right? DDS. Anyway, so it's basically low pass filters, right? Are getting the idea? Okay, let me show you one simulation really quick. So this is a low pass filter. I'm creating a pulse. It's 50% duty cycle. So I'm going to run this. So that's V in. Let me label it. So if I run it, so V in just the 50% digital signal, 0 to 5 volts. Okay. See? So let me ask you a very simple question. How can you fully charge the caps? How could you do that? You are not changing the customer's signal frequency, right? That's the customer's requirements. You have to change the circuit design. So what can you change to make it fully charged?
Lower the capacitance.
Yeah, lower the capacitance. Let's change it to 1 nano. Ooh, it's giving me a digital output. Is it perfect?
No,
It's fine.
it's pretty good.
Thank you. Thank you, LTSpice. So how do you measure the time delay?
0.7 RC.
That's how to calculate it, right? But how to measure it? 50%. Okay. So 5 volts. So find out 2.5 volts. Look at it. So 2.57. Let me make it 2.5 exactly. I can't, but very close, right? 2.7, and I click one more time. Get another cursor. I point to the input. So eventually get a delta T. That's the horizontal delta. It's this guy, right? 78 microseconds. If you do a 0.7 RC, they are all ones, right? So 0.7, you can expect it's going to be 7 something, right? So if you do the calculation, it should match the theory. 78 microseconds, right? So it's going to be challenging to create a series of PWM waveforms in LTSpice. It's used for different purposes. But eventually, you can imagine if you can create a series of PWMs like this, you will be able to create a sine wave eventually. So for the playback experiment for lab 10, the sampled, so the ADC is doing sampling for your microphone signal, okay? How that works, let's think about it. So the microphone signal is getting sampled. Let's go back here. Here's the microphone, right? Remember it played back my voice. So this one, the first order low pass filter sampled my voice, and then injected the signal to RA5, which is AN0. Oh, there's one thing I need to fix on my website. I probably didn't include the ADC module in the Lab 9 instruction, but I did have it in my project folder, so I have to fix that snapshot. It's confusing people. Anyway, so you do need, whenever you need ADC to sample your voice or any analog signal from the environment, you do need ADC. Keep in mind. So RA5 is connected to AN4, which is AN4, the fourth channel, the fifth channel of the analog, the ADC module in the chip. And then it's getting digitized. And it's giving you what? Giving you bytes. Okay, so every single one, remember which register is holding the bytes? The ADR something H, right? So that one holds the bytes. And that bytes was directly saved in the SD card. And for lab 10, if you look at it, do we need a transfer function? For example, the bytes, how do we convert that byte into a PWM duty cycle for the speaker? Think about that. There's no transfer function. That's why what I was wondering. It's super simple. You sample your voice as a byte. You store in the SD card. And you directly throw that byte to your PWM. And that worked. It's just the same byte. Okay, so we are doing lab 10 this week. Pay attention to that. See here. No, not that one. See if I have that piece of code over here.
So if you talk too loud, it'll saturate and what you get out on the end.
Yeah, that's a good point. I think so. Yeah.
So is the point then that the PWM doesn't have to be automatically modified since you already have the bits?
No, that's a good point. That's what I'm talking about.
Okay, just
Yeah.
wanted to clarify.
Yes,
Yeah.
yes, yeah. That's what I was wondering, but when I was looking at the code, no. So I think what really happened is you can play a song at different sections. I don't know music, at the keyboard. You can play the same song on different sections of the keyboard. You know what I mean? It's a different pitch, right? So you can play at the high pitch, but the same rhythm. So I think what that happens is, if you just use that PWM, it's just relative. It's just defining all the differences between the notes. So eventually that's why you can, when you hear from it, it still looks like what you just spoke to the microphone. But it might be a different pitch, but you couldn't really tell the differences. I don't know if that makes sense. So you can play it's the same song with different pitch at a different section of the keyboard. I think that's the same concept over here. So that's everything about Lab 10. You ADC it and store the bytes in the SD card and take it out and directly plug into the PWM. It's going to directly play it from the speaker. It's really interesting. All right, so I'll see if there's anything else I need to talk about for Lab 10 on Wednesday. But today we need to move on with the DDS. So look at your in-class exercise. If you don't have the time to finish everything, I'll let you submit it on Wednesday. Right? Let's take a look. That's the learning targets for today and Wednesday. Okay. The first one is easy, right? Did you finish it? Okay, 1/2πRC. What about second one, DDS? So what happens is, so when you are doing generating a sound wave, you use a lookup table. So a lookup table is just a ROM, read only, memory. These are in the old days memory files, but now they are all registers. Don't worry about that. Like ROM, sometimes you see RAM and all these kind of things, but they are all used as registers in here. So we're not really having any differences. But the thing is, we're not writing to them. We're not letting the customers or the user to write to them. So we pre-store. For example, we have from 0 to 2 to the 10th minus 1 this many bytes in there. Okay, it's 10 bit. So there are totally 1023 from 0 to 1023 registers, and every register is 8 bit. Okay, so every byte store a value. How many periods do we need to store in that look up table? LUT. It's basically just cheating, right? So you pre-store the values in there, so you don't have to do it all the math every time. It's a really common method being used in digital circuits. How many periods do you need to store in there if you want to form a sine wave? The sine wave has to, sometimes you need a, different length, right? The customer may need like 5 periods, 10 periods, 1,000,000 periods, doesn't matter. But how many periods do you need to store in the lookup table in order to achieve it? To let the user take out every single point and form a sine wave. Series of sine waves or one sine wave, doesn't matter. How many periods do you need to store in here? Which is the amplitudes of the points. 0, 0.5, 0.62, whatever. So these points, right? So these points are being stored in here as a value. How many periods do we need to store in the ROM for that purpose?
I mean, we store 1024 because we have that many.
No, 1024 is that many of points. That's a resolution, depending on. So, if you have peak-to-peak voltage, for example, 5 volts, that's a resolution, which means the differences between these two can be as small as what? Oh, 1024, sorry. That's a resolution. It means how fine your sine wave will looks, right? If you have only like 16 entries, your sine wave will look like stairs, like this. I mean, it doesn't look good, So you need more entries to form a more smooth sine wave. But how many periods do you need to store in here? Or how many periods necessarily need to be stored in here? Yeah, 1, right?
Typically only need a quarter, right? If you're willing to make
Yeah, that's even smarter, right? So just need to flip it. But usually we don't take the math. It's more computational efforts or wasting power probably. We just need to store 1. Doesn't matter. Just store 1. Okay, just store 1. So you see this figure on Dr. Carlson's website, you know what's going on right now, right? So there's no analog sine wave in the ROM. It's basically just number of points, defining all the points for 1 period, just 1 period. So when you're trying to form different length of sine waves, you just keep repeating, take the same points and assign to the output. That's it. Make sense? They are same values. What's that?
Is phase increment though like how wide it is?
Yes, that's right.
So it's like the 5 volts divided by
Let's move forward with the phase increment right now, okay? Let's see, what's the next? Oh, so for this one, how do you achieve a different frequency though? Since, for example, it's given that I'm taking out every single point every 10 microseconds. Okay? I take the first point, assign here. I take the second point, assign here, and it's 10 microseconds intervals. It's a standard sine wave being stored in here, no problem. So what if you skip 1 point, but are still taking out points every 10 microseconds, but you're skipping. Let's say it's called phase increment, okay? Let's say phase increment, let's just use integer for now, 2. Which means you're skipping 1. So every 2 points, you send out 1 value to the output. So what's going to happen? But still 10 microseconds, okay? So intervals are still 10 microseconds, but you're skipping points. So which means you are not, so after you take this first one, you're not doing the second one. You directly jump to the third one.
So you cut the frequency in half?
Yeah, actually it's doubling it. Yeah, see? So for example, now I got the first point here, right? So still 10 microseconds, I'm taking these points. See, it's jumping higher for the second point. So eventually, you're getting higher frequency. It's basically like a squeezing the original frequency, squeezing it. Since you are jumping, skipping by 1, it's actually the phase increment. The phase increment number is 2, which means what's that?
We're just counting the samples every other sample then?
Counting. What do you mean by counting?
I mean, we're like index.
Oh yes. So you're taking index wise. You're just taking out, for example, it's +2 instead of +1.
Okay.
So index plus 2 by taking them off. But we don't care about that for now, I think. We just, yeah, what's up?
How would you do this without an integer value? Like, how would you determine which points jump to next if you were not using an integer?
Oh, yeah. So that's, so the thing is, integers are skipping by 1, right? But if you got, like, for example, what we have on the paper, 1.92. So we just have to use integers, integer part of it. And then there's another parameter called phase accumulator. So even though we are not getting super accurate numbers, we are rounding that to the nearest integer. But eventually, with that accumulator, you are still manifesting that results, the more accuracy eventually. It's like, have you used Excel sheet for all the adding features, right? So if you don't want to run it in the middle. So for example, you're getting 1.52 plus 1.32, something like that. You don't run it in the middle. You still keep all these original numbers, but eventually you can run the final number, which is giving you a more accurate number. If you run every single intermediate number in the middle, like 1.52, let's use 2, right? 1.3, let's use 1. So eventually you are getting an inaccurate number. It's just getting more errors. You know what I mean? So you are accumulating. This is just a number being used in the C program. You run it to the nearest one. I think this one is probably going to be, you just plug in, and eventually you get the results. Let me show you this example, okay? So it's more easier to understand what's going on. So for the first one, 10 microseconds. If it's 2, what's going to happen? What's the frequency? F out equals what? Let's see. If we have, I'm giving you what? How many? 64 entries, right? So which means 64 entries. So for the original sampling intervals is 10 microseconds. So totally, what's a period of one sound wave? It's gonna be 64 times what? 10. Okay? If you got a phase increment of 2, it's increasing that frequency by 2, right? Make sense? For now, in theory, eventually we'll run it to the nearest number, but now we just don't worry about it. We just take 1.92 for the calculation, okay? So we get the output frequency. Make sense?
That's for 2.
So why are we dividing by 64 by 10?
We're not dividing, we're timing times that one, because this is, we're skipping that by 2, skipping every single one, where we're taking every point from 2. So it's doubling. If it's 2, it's doubling the frequency. So it's 2 times the frequency. Yeah, because this is a period, right? And this is the frequency.
Yeah.
So if you're skipping 1, you're doubling the frequency, you times 2. Make sense? What about the next? Given that a DDS system with an update rate of 10 microseconds is outputting every point every 10 microseconds, and it's a 64 entry ROM, basically same thing, right? So it's given the output frequency is given, which is 8.5K. That equals, so the phase increment times the frequency, original frequency, which is 64 times 10 microseconds, right? So you can calculate the phase increments that you should use to achieve it, right?
So when you actually go to implement that phase increment, how do you do that? Because if there's like integer values in the ROM, how are you going like 1.92?
Because there's no fractional numbers for the memory address, right? You just have to round it to a nearest number.
Okay.
But the thing is, I think that's where the phase accumulator works. So that one accumulates these fractional numbers, which is something you can use fractional numbers in there, and eventually that one outputs a phase increment for you. So it's not constantly like a 2. For example, if it's 1.9, so it's not actually give you 2 all the time, but it's doing the accumulator, doing the fractional number rotations, but eventually output the nearest number as a phase increment. So it's changing. What's that?
So for the example of 1.92, like
Yeah.
on the first go around, it would go one step. But on
Yeah.
the second go around, the accumulator would have 1.8.
3.8, right? It's
So
3.8, yeah.
So it'd go 2 steps for the next one, and then another 1 step, and
Yeah,
then 2
yeah,
steps.
it could change. So that's why where we use a phase accumulator, doing all the fractional number rotations. That's why I think we have to introduce the fixed point numbers to deal with fractional numbers. You can see the following questions are addressing that. So if you move to number 4, problem number 4, you just have to tell the computer which kind of format you are using. It could be floating point, could be fixed point. So we're only learning fixed point, so which is representing fractional numbers in the memory, because the memories are only storing 1 and zeros. It's like a 2's complement. We tell the computer we are using 2's complement, then it's going to treat the first one as a sign, right? It's same for the fixed number, fractional numbers. You just have to tell the computer, hey, this number, like for example 11000011, physically this is not a fractional number. 1 is 1, it's logic 1, like 0.0 volts. Okay? You just have to tell the computer it's pre-programmed within a certain digital circuit. It's going to be processed in that certain process. For example, you tell it this is using a 4.4 fixed point format. By definition, it's really simple. So if you tell the computer, I'm following this format, these rules, so this number is not going to be that integer anymore, whatever the integer you are seeing this anymore. So this becomes what? It becomes 1100.0011. But just have to tell the computer I'm following 4.4 format. Does that make sense?
You not only need for 4.4 because you have your sign getting required.
Sign what required?
Doesn't fixed point have a sign?
Have a sign. Yeah, depending on if it's sign or unsigned. I don't know yet. That's a good question. I think for the examples we have, it's unsigned. Let's don't worry about signs for now. Okay. So, does that make sense? 4.4 format, you are leaving 4 digits after the point, and you are leaving another 4 points before the points. If I'm saying, hey, follow 6.4 format, so just adding 2 more zeros in front of it. Okay? So let's see. Interpret this number, this digital number, as a 4.4 format. You know how to do it. Okay? What do you mean by interpret? It's just this thing. This is what you see in the memory. Okay? What you see in the memory is the physical number stored in the memory. It's a register. You got all the digital binary bits stored in there, like 0.0 volts or 0 volts. Eventually, you just have to interpret it as a 4.4 format, a fixed point number. So you just have to add a point in the middle. Okay, let's keep it and turn it on Wednesday. Okay, cover more on Wednesday.